Hi, I'm Anna Stobo and I'm a Senior Research Scientist at CPI. I'm here to talk to you about a poster titled A Statistical Approach to Ink Formulation. This was carried out as part of a Horizon 2020 project called LEBED, which aims to enable the use of hybrid electronics in a series of applications by developing novel materials and processes. The purpose of this work was to optimize a copper inkjet ink for printability and stability by varying the solvents and the solvent ratios. So we started off with a base copper inkjet ink formulation, which was showing poor stability and wetting. We selected 12 candidate polar solvents based on their boiling points and their low safety category. However, this is quite a large number of solvents to look at in any sort of great detail. So we reduced the number of solvents by discounting similar solvents using principal component analysis, which is a statistical method used to compare the parameters of solvents. So we looked at how chemically and physically similar they were, and just selected 5 from that initial 12. From there, we developed a design of experiments. The idea was to explore the formulation space, so to understand the impact of each of those solvents individually and mixed with one another, so the 1-to-1, 1-to-1-to-1 ratio, etc. Following on from that, we carried out the experimentation using ChemSpeed Formax high throughput robot, by dispensing components and mixing using high shear mixing. The advantage of using high throughput robotics is that you get reliable dispensers each time. You can make a large number of formulations in an automated manner without taking up technician or scientist time. So these components were dispensed, mixed using high shear, and the resulting inks were characterized. Again, much of this characterization was carried out in an automated manner. So the 3 automated methods were rheology, light transmission, and TGA. The rheology was used to determine that the viscosity of the ink would be within the right range for inkjet printing, which is usually up to 14 millipascal seconds. The light transmission was used to measure the dropout of particles, so the sedimentation of those particles over time. As the particles drop out, the tops of the vials become more transparent. And TGA was used to measure respective drying times. We also looked at microscopy to carry out imaging of the wetting of the droplets. So the outcome of this DOE was that a formulation was recommended based on our required outputs. So we put in a target range for viscosity. We aimed to maximize stability, maximize drying times to prevent ink drying on the inkjet cartridge, and maximizing wetting onto a substrate. The final formulation was produced in replicate, and this confirmed statistical findings. And this resultant formulation did achieve the set requirements. So really, this process demonstrates how you can use statistical methods and high throughput experimentation for this discovery phase of ink formulation. And this will give you a more targeted approach to optimization. Thank you for your time.